Hi, everyone. Thank you so much for joining us today. I'm really excited to be chairing this lecture. So I will introduce myself very quickly and then I'll hand over to Raghu. So my name is Sarah Thomas. I am an associate professor in the Department of Engineering and also a tutorial fellow at Balliol College. And yeah, I'm very excited to chair this session today. So we are going to be hearing from Dr. Raghavendra Srinivas, who is a research fellow in the Department of Physics. He's an experimental researcher working on using trapped ions for quantum information processing and quantum sensing. Raghu did his PhD at NIST, the National Institute of Standards and Technologies in Boulder, Colorado, working on ion storage. And then in 2022, he joined the Oxford Ion Trap group of Professor David Lucas as a postdoc. And there he demonstrated the world's first quantum network of entangled optical atomic clocks, which we'll be hearing about today. Raghu is a quantum technologies early career fellow, working on these trapped ions for quantum enhanced metrology. And between 2022 and 25, he was also an early career fellow at Balliol, teaching the physics students here. So over to you, Raghu. I'm very excited for this talk.
No, thanks a lot, Sarah, for the very kind introduction. So let me first pull up my slides. Can I just check that the slides are working and you can see my laser pointer as well?
Yes.
Okay, great. No, so thanks again, Sarah, and thanks to the Balliol Development Office for organizing this. It's always a pleasure to do something with the college. And as Sarah mentioned, so I've been working with trapped ions for more than 10 years now, and we've had quite a few different adventures with them. So here in this talk, I'll be focusing on the more recent one since I joined Oxford in about 2020 or so, where we were playing around with clocks, springs, and qubits. A quick overview of what I'll be talking about today. So first, I'll give an overview of quantum technologies and the two phenomena that underpin them, superposition and entanglement. I'll give a brief description of trapped ions, how they work, how we trap them, and then I'll go into three of the more recent projects that I've been involved with. So on the clock side, as Sarah mentioned, we demonstrated the first network of entangled optical atomic clocks. For springs, we develop new interactions, squeezing type interactions on the motion of the ions, which can be seen as quantum harmonic oscillators. And finally, I'll be talking about using these ions for quantum information processing and quantum computing with ions. And this includes some of my work at Oxford Ionics, which is a spin-out from the university group. So you might be surprised at how much you interact with quantum technologies already on an everyday basis. So one very pertinent example is just Google Maps. And here you can see I'm just having the directions from the Beecroft where my office is to the college. And here, we have Google Maps is telling me that I'll take about 12 minutes to walk there. And in order to do this, I'm relying on GPS satellites that are roaming around the Earth. And in particular, I'm relying on a signal that goes from my phone to three of them. And by looking at the time difference between when it reaches these satellites, I can then figure out where I am. But in order to do that, I need the timing resolution afforded to us by atomic clocks. So that's one example of a quantum technology already. Even just going to Tesco's, when you're scanning your items, that's using a quantum technology. So that barcode reader has a little diode in there that has a laser that it uses to scan the information off the barcode and tells you what items you're buying. If you've ever had to use an MRI machine, that's another example of a quantum technology. But of course, we should also be a little bit careful, and all that glitters isn't quantum, and there's some examples that are less quantum than others. So maybe very briefly, what does it mean then for something to be quantum? So at its core, what it means is just that there are some quantities that are no longer can be described by continuous variables, and they just have to be discrete. So here, for example, it could be the energy levels of the atom that we're using here to encode the information. Here, I've just labeled them as our two states, 0 and 1. It could be used, for example, in photons, which are now single particles of light. So it's no longer just a wave, but you can also be discretized to single particles. And that's something that Sarah has been working on for a bit. And you might think that this is somewhat esoteric and it doesn't really impact you on a day-to-day basis. But even if you're working in English literature, for example, this could have serious implications. So grammatically, where before you might say that there was less light, you would now be compelled to say that there are fewer photons because now they're quantized. One of the key properties of these quantum states is that they can be in the superposition. So here they're no longer just 0 or 1, but they can be both 0 and 1 simultaneously. And in general, they might not be an equal superposition of 0 and 1. And to describe them mathematically, we would have these additional coefficients A and B, which in general are these complex numbers that govern the probability amplitudes of being in 0 or 1. To give you a feel for how quickly these type of superpositions can get quite complex. So I just started off with just a simple example of one qubit, so one quantum bit, so a two-level system. But now imagine if I have multiple qubits together. So with one qubit, I have two possible states, 0 or 1. With two qubits, I have 0, 0, 0, 1, 1, 0, and 1, 1. So 4 states. With 3, I have 8 qubits, 8 different states. And once I get to the point of about, let's say, 300 qubits, there are 2 to the 300 possible states. And at that point, that's more than there are atoms in the universe. It's about 10 to the 80 atoms or so. And to give you maybe a hand-wavy explanation of how this might lead to advantage when we're trying to do calculations. So one way of thinking about this is that if I'm trying to run some algorithm or function and I'm trying to figure out what it does, instead of running it on each of the different states one by one, I could run it on all of these simultaneously if I'm using a superposition state. A very special type of superposition state is these entangled states. And this is one example here where it's 0, 0, and 1, 1. And in this particular notation, what it means is that the number on the left corresponds to Alice's qubit and the number on the right is Bob's. So what this is telling us is that now I have this very specific superposition of 0, 0, and 1, 1, but now Alice's qubit is no longer independent from Bob's. So if I make a measurement on Alice's qubit, it will affect Bob's as well. So imagine I prepare this state 10 times and then I do a measurement. If I'm just looking at Alice's qubit, about half the time I get 0 and half the time I get 1, as I expect. And the same thing goes for Bob. But if I look at the correlations of these qubits, they're always correlated. So even though I don't know beforehand, before the measurement, whether it would be 0, 0 or 1, 1, I do know that regardless of the outcome, Bob's qubit will always be correlated with Alice's. And it's these type of correlations that we can use to enhance some of the measurements that I'll be talking about later. Having gone through a bit of a background on quantum physics, let's move on to trapped ions. So this is the very specific platform that I've been using for my experiments, and there are quite a few different platforms that people are using. So aside from trapped ions, people have been using neutral atoms, people have been working on superconducting qubits, and it's that kind of work that led to the recent Nobel Prize just a few days ago. And I mean, people have also been working with photons, as I mentioned, that Sarah is, and nitrogen vacancy centers, amongst others. So trapped ions are just charged atoms. So we take a neutral atom, we shine a laser on it typically to get rid of one of the electrons. And then once it's charged, we can now trap it with a combination of static and oscillating electric fields. I'd say trapped ions are a relatively mature technology. So the Paul trap, which is one type of trap that people have been using, was developed back in the 1950s. So people have been trapping these particles at a while, though it's been more recent that we've been controlling them at the single atom or single quantum level. there are a few different types of traps that people can use. So one example is the Paul trap that uses a combination of static and oscillating electric fields. So here we have this is the classic like macroscopic Paul trap with the 4 different rods. So we have the 2 opposite electrodes here that have the oscillating voltages, and then we have the static voltages provided by these 2 other electrodes here. And more recently, people have been thinking about collapsing all of these 3D structures that you need onto a surface, where now you can make use of developments in microfabrication technology to make these type of traps, which becomes important as you think about scaling these devices to more and more qubits. And as I get to in the later part of my talk, it's also quite useful to have these surface electrode traps because now we can trap the ions very close to the surface. So about 30 microns compared to the few hundred microns, or about a millimeter that we have with these macroscopic traps. And then here, by trapping them very close to the current carrying electrode, we can get a significant magnetic field and magnetic field gradient that we can then use to manipulate these qubits and also entangle them. In terms of the ions that we trap, mostly we work within group 2 of the periodic table. And the reason for this is quite simple. So here, all of the atoms have 2 valence electrons. So once we get rid of one of them, we can trap them because now they're charged. And with only 1 valence electron left, it starts to look a lot like hydrogen, which is just quite a bit simpler. And I mean, for me, anything more than one valence electron kind of makes my head hurt. So I'm quite happy with that. In terms of the different elements here, so I'd say I've worked with all of them except radium. And my current research has mostly been with calcium, strontium, and barium, though my PhD work was with magnesium. There are also a few other elements that people have been looking at. So aluminum is one that's been used for the most accurate clock in the world. The early experiments also used mercury, some later ones, cadmium. Ytterbium has been a workhorse for a lot of quantum information experiments in different groups, but also out of academia, for example, at IonQ or Honeywell. And there's also some other ions such as lutetium that people have been looking at. And of course, there are also molecular ions, so not just a single atom, but the calcium hydride, for example, and also highly charged ions, and where we don't just get rid of one of the electrons, but more of them, and that makes us more sensitive to certain effects in the atoms, and that can be used, for example, to probe properties of dark matter, among some other things. This is an example of an ion trap apparatus that we've been using here at Oxford. And this beautiful photo here was taken by my colleague, David Nadlinger, also from Balliol. And he actually won an award from National Geographic for this. So here we have so we don't quite have the rods for this trap, but we have these different blades. So this is a blade trap. And then there are these 2 needle electrodes here that provide the confinement along the axis. And if you look very, very carefully, right in the middle here, there's a single blue dot, and that's a single strontium atom or ion that we've trapped. And this photo here wasn't taken with any advanced apparatus. It was just using a normal DSLR camera. David did have to turn up the exposure to about 30 or 40 seconds or so. But I mean, it's the point that we could also even try to take photos of this with your phone. This is an example of a surface electrode trap. And this is the trap that I used for my PhD. So this is gold on top of sapphire. And as I mentioned, so with these type of traps, we get to trap the ions very close to the surface, and that also lets us put these high power currents that we use for the magnetic field gradient. So that's just the trap. What else do we need to run these type of experiments? So it turns out quite a lot of hardware, and this is just a few of the different types of hardware that we need. So here we have a giant liquid helium dewar that we use to cool down my PhD experiment to about 10 to 15 Kelvin or so for various technical reasons. And maybe just if you're curious, so as a rule of thumb, in terms of cryogenics, so liquid nitrogen is relatively cheap. A liter of liquid nitrogen is about the same price as milk. but liquid helium is really quite expensive, and a liter of helium is more about costs more like a bottle of decent wine. And for my PhD, for example, so we were using about 200 liters of helium per week, and it costs us about $10 per liter, and it's really been getting more expensive since. Here we have the vacuum system that we use for the ion trap apparatus. It's a little bit obscured by the magnetic field coils that we use to generate the quantization axis. And here we're putting in about 60 amps into these coils. And one question you might ask, well, that's 60 amps, that sounds like a lot. Do they get hot? And the answer is yes. And in fact, one of the first projects I worked on during my PhD was plumbing. So I spent about a week setting up the water cooling for these coils, because without the water cooling, this would just start to melt the rest of the experiment. Ion trapping experiments typically require a lot of different lasers. So here with magnesium, we actually need light at about 280 nanometers or so in the UV. But the way we generate it is that we start off in the infrared, so at about 1120, for example. Then we double it to 560 in the green, and then we double it again in the UV. Here we have the 3 amplifiers that we're using for the control signals at about 5 megahertz. That gives us these strong magnetic field gradients. And it might be a little bit hard to see, but if you notice, they're labeled after the Powerpuff Girls, so Blossom, Bubbles, and Buttercup. We did consider naming them after Daenerys' dragons in Game of Thrones, but then season 8 happened and we weren't particularly happy about that. So that's the hardware. What about the software? So here at the experiments at Oxford, but also at my PhD group at NIST, we've been using this open source platform, Arctic, for both the software and the hardware, and it's really matured quite a long way now. And I mean, you might recognize this view here. So a few months ago, I was invigilating one of the exams in the hall. And while I was invigilating, I was actually also running experiments remotely on one of our systems. And here you can see these 2 bright dots for each of the atoms. And here we were actually running some of the entangling experiments that I'll be talking about later in my talk. So I mean, they're really at the point where a lot of the procedures have been automated and we can run them remotely really quite reliably. So this is an example of Rabi flopping on our qubits here with magnesium. So all this means is that it's flopping from 0 to 1 back and forth. And here we can see that it's really quite a clean signal, and it follows the theory almost exactly, which gives you an idea of how nice trapped ions are to play around with. And I remember quite vividly when we first got this type of signal in the experiment. And I mean, on the face of it, I mean, it's just quite simple, right? It's just a sinusoid. But I'd only read about Rabi flopping before on the textbook, and I've never actually done it experimentally. And here we're at the point now where we can control these single atoms and manipulate them so precisely that we get these type of plots that you could just generate, or I mean, look identical to what you'd find in the textbook. All right, so I'd like to move on to one of the 3 projects that I'll be talking about today. So this is on the clock side, where we entangle 2 remote optical atomic clocks. And here I'd just like to highlight that the lead student on this project was my colleague, Beth Nickel, also from Balliol. I mean, he did a fantastic job on these experiments and has since graduated and left the group. And to maybe just give a bit of a background here, so optical atomic clocks are one of our most precise tools to measure time and frequency, and really, they're one of our most precise rulers to measure anything in the universe. And to give you an idea of how accurate they are, the most accurate clock in the world using a single aluminum atom, with this atom, we're able to determine the transition frequency to better than 1 part in 10 to the 18. So to put that into context, that's equivalent to measuring the age of the universe, so 14 billion years or so, to better than a second. At that level of precision, if we're able to compare multiple such atomic clocks, that opens up a whole host of applications. We can use that to probe the properties of dark matter. We can start looking at the space-time variation of fundamental constants. We can use this for geodesy, where we're using precise frequency measurements to determine the heights of these atoms. So atoms at different heights tick at slightly different frequencies due to the gravitational shift. And here we're at the point where we can start to resolve centimeter and even millimeter level shifts. But all of these measurements, if you're making them on independent systems, will be limited by the standard quantum limit. It turns out that entanglement provides a path beyond the standard quantum limit to the ultimate precision allowed by quantum mechanics, the so-called Heisenberg limit. But before, this type of entanglement enhancement had only been demonstrated locally, so for atoms in the same system. But it's when you're able to compare atoms in different systems in different locations, so that's where the more interesting applications come up. But the reason why it hasn't happened before is that in general, getting entanglement is quite difficult already, even if they're local. It's all the more difficult if they're remote because you're now trying to generate these interactions between two very, very independent systems. So this requires high fidelity entanglement because it's not just any entanglement that we need. We need good entanglement so we get good contrast on the signal, but we also need to be able to generate it quickly. If most of your measurement is dominated by this entanglement generation, it's not very practical anymore, and you're better off just using unentangled atoms. So this is where our quantum network comes in, where here at Oxford, we have one of the state-of-the-art quantum networks in the world in terms of fidelity and rate. And here we're able to create entangled states of two remote strontium ions with a fidelity of close to 1 in an average duration of about 9 milliseconds. So this 9 milliseconds in context is short compared to the typical probe durations that people use for clock experiments of about 500 milliseconds or so. And alongside these clock experiments, my colleague David Nadlinger was also leading experiments on quantum key distribution, which is more towards the cryptography side of things. So here's an overview of the quantum networking experiment. So here we have two ion traps, Alice and Bob, separated by about 2 meters. And here we have the 674 nanometer laser that we use for the clock transition that we want to manipulate. And here, even though the atoms are separate, they're still linked photonically, which is how we're able to generate the remote entanglement. So what we do is that we simultaneously excite both of these atoms. They decay, and they emit the photons that the emitted photons from the atoms. We can then collect through these high-NA lenses. We can then pipe them over through this fiber through a Bell state analyzer. So there's a beam splitter, a couple of wave plates, and then by making measurements of the photonic state, we can then project into an entangled state of the two atoms. And the reason for this is that when the atoms emit their photons, the polarization of the photon is now entangled with the final spin state of the atoms. So then by making this projective measurement, we then get an entangled state of the two atoms. So essentially, we're using the light that they emit to make them talk to each other to get this entanglement. So what I showed you here is a very neat and orderly schematic. So this is what it actually looks like in the lab. So we have Alice, Bob, separated by about 2 meters, and all of the different optics that we need so that to make this experiment work. And it might look very, very complex, but something to bear in mind is that this didn't just happen overnight. This took many people working over 5 to 6 years to put this together and to make it work. And when you're actually working on this, then it's easier to see what all the different components are and what they're doing. But essentially, all of these different optics are to get the light at the atoms at the frequencies that we need them to be. And so through this experiment, we were able to show that we could get entanglement on this clock transition. And as a proof of principle, we were also able to show that with this entanglement, we were able to get this increase in precision that we expected, but we wanted to measure it compared to the unentangled state. And here, for measuring the frequency difference between the two atoms, you can see that with entanglement, the uncertainty on the measurement is quite a bit smaller than what we obtained without entanglement. All right, moving on to the next part of my talk. Instead of clocks, we'll now be looking at springs. In the motion of the ions that are now modeled are these quantum harmonic oscillators. And with these quantum harmonic oscillators, you can think of them as a ladder of different states that are equally spaced by the oscillator frequency. So instead of only 0 and 1, there's this infinite ladder of states that it could be, and they're all separated by the same amount, or at least ideally anyway. So these type of quantum harmonic oscillators are ubiquitous in physics, and they can be used to model many different types of phenomena. We can use it to model electromagnetic radiation. So individual particles of light can also be seen as quantum harmonic oscillators. And also the vibrations of particles and neutral atoms, nanoparticles, and of course, trapped ions. And the excitations of all of these different systems are bosons. So in the same way that photons are also bosons. Maybe taking a step back a little bit, if I think of a classical spring. So here I just have a block attached to a wall, and excuse this very poorly drawn spring here. I can, if I start pushing it, if I give it a little bit of a push, it'll go into this harmonic motion. And I can think of its motion in phase space, where I'm plotting the momentum of this block versus its position. So at this point here, when it's not extended, it's moving to the left. So then it has this negative momentum. And as it keeps moving, it compresses, and then its momentum goes to 0. So it has no more velocity, but now with this negative displacement, and then because it's compressed, it starts moving the other direction. So the momentum increases. And finally, it gets to its final point with the maximum displacement before it goes back into this harmonic motion. With this classical picture in phase space, I know where the particle would be at any point in time. It's completely deterministic. But that's not the case for a quantum harmonic oscillator, where now everything starts to get a little bit fuzzy. So the particle is no longer in a well-defined point in phase space, but more like a blob. And it now has this probability of being in these different momentum or position states. And this is where Heisenberg's uncertainty principle comes in, that tells us that there's some minimum level of uncertainty to which we can know both the particle's position and its momentum. There are ways around this uncertainty principle. So for example, through squeezing, where instead of just having it symmetric in momentum and position, you can think of squishing it along one of these directions. So in this case, it's longer along the momentum, but shorter along the position. So I can minimize the uncertainty in X, so I can know the position more precisely. But the price I pay for this is that now my momentum is more uncertain. But depending on the specific application, you can still gain a quantum enhancement. And this has already been used to enhance measurements. So for example, with the very famous measurement of gravitational waves with LIGO quite a few years ago. And more recently, we've also been able to show this in our group with the detection of small electric fields. So that's one type of squeezing, which is very much a second order process. And there are these higher order squeezing processes as well that give you different types of phase space blobs. And once you get, so squeezing is a second order process. So here are the creation and annihilation operators for the bosonic modes of the quantum harmonic oscillator. And when n is greater than 2, so it's, so for example, 3 or 4, these states start becoming quite different. And one example is that they're no longer Gaussian. So they are harder to simulate classically. And these type of non-Gaussian interactions are an essential ingredient if you want to start thinking about encoding information in these quantum harmonic oscillators instead of just the normal two-level states. However, these type of high-order squeezing interactions are not so easy to generate. So typically, you need very specific hardware for very specific interactions. And the state of the art was, or at least before some of the recent work, was tri-squeezing in superconducting systems. So a few years ago, working with my colleague Tyler Sutherland, we came up with an idea of how we might generate these higher order interactions with these with trapped ions using tools that were already there. And we were able to show this experimentally recently. So this is led by my former colleague Vana Basavan, who recently defended a thesis and left the group. And one of the big results in her thesis project is that she was able to show not only squeezing, but tri-squeezing and quad squeezing. So here is an experimentally measured Wigner function. So you can think of it as like a phase space description of the atom. And here we have the signature of squeezing. And on top, we have the experiment. Below, we have the numerical simulations to see if there's some agreement. So we have squeezing, tri-squeezing, where now we get this three-pronged state that we expect, and quad squeezing. So to the best of our knowledge, this is the first demonstration of tri-squeezing across any platform, and tri-squeezing in an atomic system and quad squeezing in any platform. And to give you an idea of how new it is that if you Google quad squeezing, this is probably what you will get. And I'm hoping that this will change once our paper is published, but I'm not overly optimistic. To give you an idea of how much that new scheme that we developed helped, so here we're plotting the increase in the interaction strength compared to conventional methods of generating these interactions versus the squeezing order. And with just squeezing, we gained about a factor of a few in the interaction strength, with tri-squeezing about an order of magnitude, and with quad squeezing, we win by a factor of about 300 or so. So this is just another way of saying that without this enhancement that we get with this specific method that we're using, these type of interactions would have been completely unfeasible in our system. And because now they have these appreciable strengths, we can measure them past the noise induced by various decoherence mechanisms in our trap. More recently, we've been extending that a little bit further. So what's quite nice about these interactions is that they're also spin dependent. So then by starting in the superposition of the different spins, we can now make, and in combination with mid-circuit measurements, we can now make superpositions of these different oscillator states. So for example, we can make superpositions of two different squeeze states. So one squeeze along one axis and the other along the opposite axis. So again, on top is the experimentally measured Wigner function, and below are the simulations. So here we have these two type of superpositions. So this is the even, where it's squeezed plus anti-squeezed, and this is the odd. So this is squeezed minus anti-squeezed. And it's really these odd superpositions that have these remarkable Wigner functions that even go negative here. And so we did this for squeezing, tri-squeezing, and quad squeezing. And we can see pretty good agreement between the experiment and simulations. Of course, it gets worse as we go to higher orders, as the interactions get worse, and then here we get hit by the noise more. And when we first showed this type of data to theorists, they were just amazed at the type of states that we were able to make. And it's just another example of how clean trapped ions are as quantum systems to play around with. And I think these type of experiments would really be quite difficult on other platforms. Right, finally, I'll be talking about qubits and quantum computing. So first, I'd maybe briefly want to talk about why we might want to do this to begin with. So there's been a lot of hype about quantum computing, and largely this is because we can, with a quantum computer of sufficient size, we would be able to perform calculations that would be completely intractable to a classical computer. So a quantum computer is not going to replace a classical computer for all of the everyday tasks that we have. They're going to be useful for a very specific set of problems. But even within that restricted subset, there are some very useful ones. So there's, of course, cryptography, which gets a lot of attention, especially for the military, where we can use this to break the encryption that we use. So for example, in the messages that we send, we can use it for drug discovery, in chemistry. And for me, one of the most exciting applications is actually in fertilizer production. So about 3 to 4% of the world's energy is used to make fertilizer, in particular nitrates, where we need to combine nitrogen and hydrogen to make ammonia. So this is done through this industrial Haber-Bosch process that requires high temperature, high pressure. You need some really expensive catalysts, such as I think platinum or palladium, one of those two. But in the meantime, there's this bacteria in the ground that has this enzyme nitrogenase that can do the exact same thing at room temperature and pressure, but we have no idea how that works. But we think that if we have a quantum computer of sufficient complexity, we can then use that to elucidate the mechanism of this enzyme and then use that to improve the energy efficiency of fertilizer production, which of course would have a huge impact on the agriculture industry. Quite often, if you're working in quantum computing, you're asked to make predictions of what the future might look like. And here, I'd maybe try to draw an example back to the early days of classical computing, which is kind of where we are now with quantum computers. So here, Charles Darwin, so not the same one from The Origin of Species, but I think his grandnephew or something like that, who was working at NPL, said, "It is very possible that one machine would suffice to solve all the problems that are demanded of it from the whole country." And of course, now even a single person has more than one computer between laptops, desktops, the computers that are on their phones. And I think here maybe my larger point is that with the development of quantum computers, if we can have them advanced enough, they will be able to solve some very specific problems. And the more we can develop them, the more people I think will also find different applications that we haven't even dreamed about yet. So why aren't we there yet? So in general, quantum states that we need to manipulate are very delicate. They're very sensitive to any noise and small perturbations. So that's why, for example, we go through quite a lot of trouble to put these ion trap systems in a vacuum to isolate it. Then we also worry about electric field noises. These charges are very sensitive to those. And of course, it's one thing to have a simple system with 1 or 2 qubits, but now we're at the point where we have to try to think about what does a system of like hundreds, thousands, or even a million qubits looks like. And as you add more and more qubits, you also want to keep the fidelity of the fundamental operations good. There's no point adding more qubits if they just keep getting worse and worse. And in particular, a big bottleneck in many of these systems is the fidelity of the entangling operations. So really, that's one of the key challenges that we need to solve. And that's something I've been working on since my PhD. So typically, to generate entanglement in ions, you'd be manipulating these atoms with lasers, but they have but that can be challenging to scale as it's hard to control the amplitude and phase stability of these lasers, but there are also some certain fundamental errors depending on the scheme that you're using. So for example, from photon scattering that you can't really run away from. However, if we can instead manipulate these atoms without lasers, we can eliminate these fundamental errors, these no photon scattering. And if we're using microwave or radio frequency sources, now the phase and amplitude stability are really quite a bit better because they're a much more mature technology. They have a much longer wavelength, so they're less sensitive. But of course, in order to be able to do that, we have to be able to engineer these very large currents into these current-carrying electrodes close to the ions. So for these type of experiments, we were putting in about an amp of current in each of these electrodes to generate a magnetic field gradient of about 150 Tesla per meter at the ions in order to entangle them. So during my PhD, we were able to demonstrate this new scheme of entangling these ions without lasers, and it worked pretty well, and we were able to demonstrate one of the highest fidelity entangled states across any platform. But of course, this was just still, again, with an isolated system of 2 qubits. So since about 2021 or so, I've been working part-time at Oxford Ionics, which is thinking about using this same laser-free technology to scale it up to a larger system and to build these large-scale ion trap quantum processors. So this is a spin-out from David Luskas's group, led by Chris Ballance and Tom Hardy. So Tom Hardy, I think, was also from Balliol. And here we're really using these laser-free techniques to not only do the single qubit rotations, but entangle the ions. So we got a 30 million Series A in 22, and more recently have been acquired by IonQ. As I mentioned, one of the big bottlenecks in quantum computing is the fidelity of the 2-qubit error rates, and that's something we've been actively working on. And I mean, it's one thing. So I mean, we think we can do really well with these laser-free techniques, but then we want to demonstrate this. So here, this isn't a comprehensive overview by any means, but some of the bigger companies, the commercial companies, or the commercial systems that are out there. So here, Rigetti, IBM, Google are all using superconducting qubits, and Quantinuum and IonQ are using ions, but then manipulating them with lasers. So here, the state of the art was about a fidelity of 999, an error of 0.1%, and that's something we were able to beat in 24 last year, and more recently we were able to get the error below 1 times 10 to the 4, or 0.01%. And this is this is the data that we were using to characterize the fidelity of the entangled states. So here we're doing a very specific type of randomized benchmarking where we do a sequence of multiple gates in a row. And then by looking at the success rate of the sequence or the survival of the ions in a specific state, we can then determine these errors. So here with a sequence length of 500, we're doing more than 1,000 2-qubit gates, and we have still a success rate of about 90%. So that corresponds to an error of a little bit less than 1 in 10,000. And these demonstrations were done with a system with just 2 qubits, and now we're working on scaling this up to a larger system while still keeping this really extraordinary fidelity that we were able to achieve. So I'd just like to end with this quote from Erwin Schrödinger back in 1952. We never experiment with just one electron or atom or molecule. In thought experiments, we sometimes assume that we do. This invariably entails ridiculous consequences. So back in 1952, and since then, we're at the point where we're now able to trap and manipulate single atoms. And because of all of the wonderful work that's been done in the past decades by groups all over the world, we can even start dreaming about building computers out of them. And really, it's been such a privilege to be in this field and to explore these ridiculous consequences on a daily basis. all of the work that I've been talking about today wouldn't have been possible without the fantastic teams that I've had not only during my PhD at NIST, but also at Oxford. And here I just especially want to highlight David Lucas for building such a fantastic group. I mean, it's such a pleasure to come to work every day. And I mean, with David, especially, he's given me so much support for the type of work that I wanted to do and the freedom to explore all of these kooky ideas that I've had. And of course, I'd also like to thank my colleagues at Oxford Ionics that made all of the last few pieces of work that I was talking about possible. And with that, I'd like to thank you for your attention, and I'm happy to take any questions.
Great. Thank you so much, Raghu, for that excellent talk. Yeah, really, really nice to see everything that you're doing. As someone who works in a similar field, I'm always absolutely blown away by how impressive the results are that you work on. So we've already got some questions coming through in the chat. Please do type questions in the Q&A and I will read them out. So we've already got a few, so I'll jump straight in. So the first question is, if trapped ions are very short-lived, would a quantum computer have to perform calculations in short bursts of activity? And would that limit the complexity of problems that can be solved?
That's a good question. So I didn't really get to talk about the lifetime of the ions in the trap. So I'd say, and this is part of the reason, for example, why we want to cool them to lower temperatures to begin with. So the lower the temperature we can get to, the better the vacuum pressure in. So the less crap you have in the vacuum that can hit the ions and knock them out. So I'd say now these systems are really getting quite well engineered, and at the company, for example, we're able to keep ions for days at a time, even in these surface traps. So it's true that we might be limited at some point once we get to these longer and longer complications, but it's certainly not a limit that we've run into already. And I think even then, there are ways around it where you can start encoding the information in multiple atoms, so you have these redundancies in case you lose one of them.
Great, thank you. Can you speak to the possibility of quantum information processing in biological systems?
So just to clarify here, would this be then quantum information processing using biological systems, or to find out about biological systems? I think it's maybe the former.
I guess the former. If not, please could the person
Okay.
maybe correct?
This is a fantastic question, and what's actually quite cool is that there's this whole field called quantum biology where they're investigating quantum phenomena in biological systems. And one really cool example of this is avian magnetoreception. So how birds are able to, so migratory birds such as European robins are able to determine where the magnetic field is in order to, go to warmer places during the winter. So through a whole series of experiments that have been done over the past 2 decades or so, they've actually been able to determine that it's very much a quantum mechanical process that's happening in the eye of the birds, where there's this particular molecule, cryptochrome, where if you hit it with a specific wavelength of light, it will become this free radical, which you can think of as just like a free electron that now precesses in the magnetic field. So depending on the orientation of the magnetic field, it will precess in a certain amount, and that will result in a separate chemical process that the bird's able to detect. And I'd encourage you to look this up after the talk, and I'll maybe provide a link and maybe ask if Dave could share that. But they were able to do experiments that showed that this process was unambiguously quantum mechanical. And I mean, they're still in the process trying to figure out how exactly it works, but this is remarkable because now it's in this room temperature, this very wet and noisy environment, but it's still able to keep its coherence long enough to have a very real application. And in terms of the other type of biological phenomena with this, there's also photosynthesis, where the light hits one part of the chlorophyll molecule and then goes into like a superposition of different excitations to converge to where it needs to be. And yeah, I mean, it's an area of active research. I'd say in terms of being able to use it practically, for us, I think we're quite far away because we don't even really understand how this works to begin with at the detail level before we can think about how we can use it. But I mean, certainly it's very cool to explore.
Very interesting, thank you. How is the squeezing generated?
Yes, I didn't really get to talk about the squeezing. So there are a few different ways that you can generate the squeezing. One way of thinking about this is that I'm modulating the potential well in which I'm trapping. So you can think of it as I'm changing the frequency of the harmonic oscillator at twice its natural frequency, and that gives you some of these squeeze states. Maybe a more, and I should say maybe specifically for our case, what we're doing is that we're using lasers to create these interactions. And there are these higher order, because the laser interaction with the ion is not uniform, and there's a spatial component to it, you can think of it as the first order derivative gives you a gradient, and then the second order derivative gives you a curvature, which you can think of as like an x squared term, which is where my a squared plus a dagger squared comes from. But maybe long story short, for the experiments that I talk about, we were using lasers for that.
Thanks. Given the strategic advantages of achieving quantum computing, should you be talking about this in public? Discuss.
So all of the results that I've been talking about have been public already. I mean, I think there's no danger there. And I'd say a lot of the secret sauce, if you will, of for example, like some of the company work is in how we implement the interactions and how the systems are engineered that aren't public.
Great, thank you. A question about what sort of software is needed to program a quantum computer. How might one create a series of instructions?
Great question. So I'll maybe start specifically for the systems that we have. So for our systems, we're using Arctic, which is an open source software. And here we start off with a Python script that gives us where we can code in the sequence of pulses that we need. And that's basically telling the hardware what to do. So with this, we're telling the laser to turn on a specific point in time, or to turn on, to open the switch of a microwave source, so then we can get these magnetic field gradients, and so on and so forth. So we start off with this. It gets converted then to this low-level language that gets sent in FPGA that now has this timing precision that we need for the hardware. And I mean, maybe taking a step back, what people are doing is, so for example, with IBM, they have this language called Qiskit, where you can code quantum circuits that tells you to do certain operations, the single qubit rotations, entangling operations, and then that gets converted to the hardware pulses that then we then implement. So in practice, what we would need is an API where the customer then, or whoever, or the user, is able to code the quantum circuit that we want, and under the hood, we're converting that circuit into the series of pulses that we need and executing it on the hardware.
Great, thank you. By using quantum entanglement, would it be possible to send information instantaneously?
Again, a fantastic question. It's true that with entanglement, we have these type of correlations that are non-local, but unfortunately, we can't use them to transmit information. And we still, even though the collapse of the wave function is non-local, in order to get any useful information out of it, you need to know what measurements have been done and what the outcomes were. So then you would still need this classical signal between your two parties, even if they're separated from long distances.
Thanks. So one of the interactions that you mentioned, you described as non-Gaussian and therefore more difficult to simulate. What distribution, if analytic, does this interaction follow, and how do you simulate it?
So if I could maybe go back to that specific slide. Yeah, so when I say non-Gaussian here, so this is an example of what a non-Gaussian interaction or a non-Gaussian state would look like. And here you can see that I can't model it with just the single Gaussian anymore. And I think it really also depends on the specific state that you're trying to interaction that you're driving. So here we have tri-squeezing, we have quad squeezing, and we're still able to simulate these systems because they're still relatively small and they don't occupy that many different states of the harmonic oscillator. But as we get to larger and larger states like this, it would be more and more intractable for our classical computer to handle.
Thanks. How accurate does the equipment of Bob and Alice need to be to enable entanglement?
In terms of the experiments that we were talking about with the clock, for example, with the entanglement enhanced clocks, so there I'd say we're a little bit less sensitive to the fidelity of the entanglement. So even if there was a 10% error, we would still be able to see a meaningful enhancement. I think it really ultimately depends on the application that you want. And more recently, we were able to show that we could distribute a quantum algorithm across this two different setups. And here we had errors of about 5%. But looking ahead, if you wanted to use this for useful computation, I think then you would really need to get the errors down to 1% or maybe 1 in 1,000 or lower. There are ways in which you can correct for some of these errors. But then the more the error, the larger your error is to begin with, the more resources you need to correct them, which is also part of the reason why we want to improve the fidelity of these entangling operations, because the more precise they are to begin with, the fewer qubits we need to do error correction, and the faster we can achieve or reach a useful device.
Great, thank you. That's all of the questions that are in the chat for now. So maybe I'll ask one of my own just while I'll wait to see if anyone does have any more. Please put them in the chat. But you mentioned towards the beginning that atomic clocks and entangled atomic clocks could maybe be used for measurements on dark matter, something that I don't know about. So maybe could you explain how that would work?
Yep.
You know about it.
Yeah. No, and I mean, I should say here, so this is really not my area of expertise, so I do have to maybe move my hands a little bit. So the idea, so we don't really know how dark matter works, even though dark matter and dark energy comprise something like 85% of the known matter and energy in the universe. There are these theories that postulate that they might very weakly interact with the transitions in these atoms, but these interactions are very, very weak, which is why they're called dark matter to begin with, because they don't really interact with electromagnetic fields. But then the idea is that if we could now measure these clocks very precisely in two separate locations simultaneously, we could see the effect of a potential dark matter wave where it moves the frequency of one of the atoms slightly relative to the other. And then by now looking at these small differences in frequency, we can then understand a little bit more about the structure and effects of the dark matter. I should say, if you want to read maybe more about this is a great review paper by Safronova et al., I think, that I'll also see if I can share a link on this after the talk.
Great, thank you. Still don't see any other questions, so maybe I'll ask one more and then we'll leave it there. So I just wanted to maybe put some numbers to it in terms of where you are with how many kind of qubits you can trap and control at the moment, and where you maybe want to get to be able to start solving useful problems. I know that's probably quite hard to put numbers to, but maybe just to give a rough idea.
Yep. So I'd say that in terms of the state of the art now, systems are at the point where we can control like maybe 50 qubits or so really, really well. And Quantinuum, for example, had quite a few recent results in their system where they were able to measure a quantum volume up to about 23 or 24. But I mean, that's still at the point where we can't get quantum advantage yet. I think we'd start seeing that more at the 100 to 1,000 qubit type level. But I mean, even at that point in time, it's already going to be very challenging for classical computers to simulate. So even though it's maybe less suitable for practical applications, it's rapidly reaching the point where it's outpacing what we can simulate with classical computers.
Excellent, exciting. Well, I could ask Raghu questions about quantum all day, but I don't see any more questions in the chat, so therefore I think we will wrap it up there. So yeah, I just want to thank Raghu again so much for an excellent talk. It was really enjoyable. And then also remind everyone that there will be another public online lecture, will be the final one of the year, will take place on the 25th of November. And that will be from Professor Vijay Balasubramania, who was the Eastman visiting professor last year. And he will be talking on Occam's razor, are simple explanations better? So hopefully you can all join again for that one. So yeah, thank you so much.
Yep, thanks, Sarah, and thanks everyone for listening and for asking all of those fantastic questions.